Am I audible? Uh, Welcome everyone for the week 3 problem solving session for the NPTEL course and introduction to climate dynamics, variability and monitoring. Today we will solve few MCQs based on the previous week. We have included the week 1 and week 2 content in our discussion today also. So, am I audible? Okay. Yes. You can unmute yourself or you can write your answer in the chat box and then we will discuss or explain the MCQs. So, this is the. So, this is the first question for today. A parcel of unsaturated air is cooled at a constant pressure till it reaches to the temperature at which the water starts to condense out of it. We have reached which temperature? So, which is the term this temperature is called? When the water contains out of it, saturation temperature, adiabatic temperature, freezing temperature and the dew point temperature. You can unmute yourself or you can write in the chat box. Okay. Oh, okay. Sorry. Is it visible now? Okay. So, this is the first question. A parcel of unsaturated air is cooled at a constant pressure till it reaches to the temperature at which water starts to condense out of it. We have reached the air's saturation temperature, adiabatic temperature, freezing temperature or the dew point temperature. You can unmute yourself or you can write the answer in the chat box. Yes, this is the saturated temperature where we have reached. So now we have to see what are the other temperatures called. So, or what is their definition. So as you know, saturation temperature is the temperature at which the air or any kind of gas is fully saturated with water vapor at a given pressure. Key point, at this temperature the air's humidity is 100%, and when you try to cool down this air further from this temperature, water condenses out. An example is the at sea level, saturation temperature for water is about, you have to keep mind what is this at sea level, what is the saturation temperature for water. And there is another temperature called the adiabatic temperature. The temperature for a parcel of air, if it is moved up or down in atmosphere without exchanging heat with its surrounding. There are two types of adiabatic temperature in the literature. One is the dry adiabatic lapse rate. Another is the moist adiabatic lapse rate. You have seen that the dry adiabatic lapse rate is higher, about 9.8 degrees Celsius per kilometer for unsaturated air, and moist adiabatic lapse rate is lower than the dry adiabatic lapse rate. And also there is a freezing temperature, that is at the temperature when the liquid turns to the solid for a given pressure. And another temperature, there is a dew point temperature, the temperature at which air must be cooled at a constant pressure for water vapor for uh, for the water vapor to condense into liquid. Question A, correct option, question 1, correct option was A. There is the next question. The least hour of daylight that is received by a location at 50-degree northern latitude is approximately 8 hour, 10 hour, 6 hour or 4 hour. You can unmute yourself or you can write the answer in the chat box. For the least hour calculation or for the least daylight hour, there is one small formula you can use. So this formula for calculating the daylight duration D in hour is 2 by 15 cos inverse minus tan phi into tan delta. And this tan phi is the latitude of the location. So 50-degree north, there will be plus 50-degree. And delta is the solar declination angle. And for the least daylight calculation in northern latitude, this is for the winter solstice, and this delta is taken to be minus 23.5 or 23.44 degrees Celsius. You can take minus 23.5 degree, and this whole parameter you have to find this cos inverse this factor in degree and then multiply 2 by 15 and the result will be in hour. You can use the formula by yourself and see what is coming. I am giving you this formula now. I'm giving 1 or 2 minutes. You can, if you have calculated, you can calculate. So this is coming like I have calculated it anyhow. That is tan phi, that is tan of 50 degree and tan of the minus 23.5 degree, that is about 0.4. And if you calculate the value, then it will come around 7.86 hours, so around 8 hours. So for this question 2, option A is also correct. There is question 2B. Which are the hottest and the coldest temperature of Earth, and also which are the hottest and coldest temperature region in the India? This is an informative question. You have to remember the information. That is, the coldest temperature ever recorded on Earth is the Vostok station in Antarctica. Temperature is around minus 90 degrees Celsius, and for India it is the Siachen glacier, about minus 50 degrees Celsius. And the hottest air temperature ever recorded in Earth is Red Valley, USA, around 55-56 degrees Celsius, and in India it is the Falodi village, Rajasthan, that is around 50-51 degrees Celsius. So you have to keep mind the most hottest and the coldest places in globally and the Earth. Also another globally in India, of course, one also another equation we were discussed in the first class or the second class, that is the Clausius-Clapeyron equation, which says that the saturation vapor pressure rises exponentially with the temperature, and the warm air can hold more water vapor because higher temperature provide more energy for the water molecules to remain in their vapor phase. You can see at about at 0 degrees Celsius there is around 5 gram per kg of water vapor. So at the 0 degrees Celsius 1 kg of gas can hold 1 kg of air can hold 5 gram of water vapor. Around 30 degrees Celsius if you can go, you can see around there is some 30 degrees Celsius there is around 30 gram per kg, this value rises. So at the 30 degrees Celsius 1 kg of air can hold 27 to 30 grams of water vapor. And in this from this figure you can see what is the dew point temperature, what is the saturation temperature. Now we will show you one plot. So this image you have seen in the weekly lecture video. That is this is the zonal mean temperature distribution in atmosphere with the function of the latitude. Latitude is given in horizontal axis, and the pressure or height and pressure and the height vertical to vertical axes for the different seasons. Two seasons has been shown here. One is DJF, that is the December, January, February, representing the time when in the northern hemisphere there is winter, and this right panel, that is June, July, August, representing the time where there is in northern hemisphere there is summertime. You can see the temperature contour here, and also what is the color bar is also shown. You can see this more redder thing is the hottest temperature in Kelvin, and more bluer thing, that is the coldest temperature here 190 Kelvin. At 273 Kelvin there is 0 degree Celsius. So you can calculate 190 Kelvin is equals to how many degrees Celsius. You can see there is a always dark patch here at the equatorial region. That is here always temperature you can see. And then white is around white temperature is around 250 Kelvin, and then the temperature is increasing to red. Now we have different questions based on these figures, so you can answer this question. So the main features what is seen in this DJF or JJA figures are the following. In the DJF figure, you can see the northern hemisphere polar stratosphere. That is the northern hemisphere polar stratosphere. Northern hemisphere polar stratosphere. That is around 25 kilometer above the sea level. Is very cold. That is around this is around 200 or 210 Kelvin temperature, reflecting the strong radiative cooling during the polar night. At the southern hemisphere, the polar stratosphere is much warmer due to being summer, with strong solar heating in upper stratosphere, that is around 1 to 5 millibar. Tropical tropopause is cold around 220 Kelvin, forming a distinct low temperature bands across the equator. Warm temperature at the summer pole, warm temperature around 280 Kelvin at the summer pole above 40 kilometers. So you can see in this figure that is around 40 kilometer above the sea level at the time of the December, January, February. The temperature is around 280, 260 to 280 at the 90 degree to or 80 degree south. So and the next figure you can see the June, July, August figure. When there is in the northern hemisphere there is summer, the southern hemisphere polar stratosphere is extremely cold. So you can see here the southern hemisphere polar stratosphere, that is around 25 uh, yes 25 kilometer above the sea level. Here around 80 degrees south, and the temperature is around 190, kind of 190 200, this kind of thing, associated with this strong Antarctic polar vortex. This is associated with strong Antarctic polar vortex. Northern hemisphere polar structure is warmer due to summer solar heating at higher altitude. So you can see the northern hemisphere, the polar stratosphere, in the northern hemisphere polar stratosphere is warmer due to summer solar heating at higher altitude. Cold tropical tropopause is still evident, but slightly in different position and the intensity compared to what is seen in the December, January, February. Strongest warm anomalies in the summer upper polar stratosphere or mesosphere is seen. We will not discuss now what is the why this is seen, but we are saying that this is seen from this image. And also there is a seasonal contrast you can see in between two figures, that is in the winter pole, cold in mid stratosphere but can be warmer aloft in the summer stratosphere due to dynamical downwelling, and in the summer pole, cold in mid stratosphere due to upwelling and adiabatic cooling, but very warm above 40 km due to continuous sunlight. The temperature gradient between equator and the pole is stronger in the winter hemisphere in the both seasons. The temperature gradient between pole and the equator and the pole is stronger in the winter hemisphere in both the season. Now there are few questions. Some questions can be answered from this figure, seeing this figure, and some question you have to answer intuitively, very intuitively. So in here are the questions. You can unmute yourself, or we will check two questions at a once, and then you can answer the question in your chat box, or it is better if you can unmute yourself and tell the answer. In December, January, February time, where is the coldest stratospheric region located? In December, January, February, where is the coldest stratospheric region located? While answering this question, first try to locate which would be the best answer. First use the elimination method. First eliminate one or two options just by seeing this latitude information, altitude information. So in December, January, February, the coldest stratospheric region is located near 60 degrees south at 20 to 30 km, near 30 degree north at 20 km, near the equator at 10 km, and near 80 degree north at 25 km. So for this question, you know one thing, that this C cannot be answered, because we know at the equator the tropopause is starting about greater than 15 or 18 km. So stratosphere comes after the tropopause. So option C cannot be our answer. And so the other three option remains: near 60 degrees south at 20 to 30 kilometer, near 30 degree north at 20 kilometer, near 80 degree north at 25 kilometer. Now we can view this map. 60 degrees south at 20 to 30 kilometer. So 60 degrees south and 20 to 30. This 25. Here the temperature is about 230. This region is around 230, 35. This 60 degrees south, 235. 30 degree north at 20 kilometer. 30 degree, sorry. 30 degree north at 20 kilometer. Here there is 210 Kelvin, 210 Kelvin, around 210, and there would be 80 degree north at 25 kilometer. So here 80 degree north, 60, 70, 80. 80 degree north around 25 kilometer. Here there is around 190 Kelvin, 210, here around 200 Kelvin. So here you got 235 Kelvin, here you got around 210 Kelvin, and here you are getting around 200 Kelvin. So the coldest stratospheric region is located near 80 degree north at 25 kilometer. For this kind of question, of course, if such questions are asked, then you will be provided these images, and we are just discussing these questions just to test how well you can interpret the images given in the lecture notes. In the question 4, at what pressure level does the cold point tropopause approximately occur? At what pressure level does the cold point tropopause approximately occur? At what pressure level does the cold point of the tropopause approximately occur? So now you have to see what is the cold point of the tropopause. Tropopause is seen around 15 or 20 kilometer above. So here you have to just find what is the you have to mentally draw a straight line from here. You can see around 100 Kelvin, 100 millibar is at the pressure level, where the coldest point, that is the more darker color, the darker blue color, is located. So this is around this darker region. So in the latitude between 0 to 30 degree or 0 to 60 degree, the coldest point of the tropopause is occurring at around 70 to 100 Kelvin, this region. Sorry, Kelvin, not millibar. Sorry for the mistake. So at what pressure level does the cold point tropopause approximately occur? So the cold point tropopause, that is the coldest part of the tropical atmosphere, is typically found near the 16 to 17 kilometer altitude, which corresponds to pressure of roughly 100 millibar in both the figure. So you can just see the at the 100 millibar there will be more darker temperature region. So you can just plot here at 100 millibar. You are getting more darker contours. So question 3D, question 400, and question 5. Which hemisphere shows the stronger latitudinal temperature gradient in June, July, August? So we have to see the June, July, August, this graph, and we have to check which hemisphere shows the stronger latitudinal temperature gradient in June, July, August. So here 0 to 90 degree, this is dropping from 200 to 280 at the northern hemisphere, and in the southern hemisphere you can see, and this is 200 and this came to 220. Yet the contours are more closely spaced, and here is 280 around. So for this question, in June, July, August, the southern hemisphere is in winter, leading to very cold polar stratospheric temperature and much warmer tropical values. This produces a steeper equator to pole temperature gradient compared to northern hemisphere summer, where polar temperatures are higher and gradients are weaker. So for the June, July, August, the latitudinal temperature gradient is more in the southern region. So question 5, option B is correct. Question 6, during December, January, February, the stratosphere is coldest over which region? During December, January, February time, the stratosphere is coldest over the northern hemisphere, southern hemisphere, equator and north pole. So when this question stratosphere comes, we would take around 25 kilometer latitude. So we have to find around 25 kilometer latitude what is the coldest temperature of the stratosphere in the December, January, February. Question 6, at the 25, this is 25. So in the December, January, February region, the coldest temperature, that is the most darker patch in this image, that is around 190 Kelvin. This is occurs at about 80 degree north, this region. So this is seen at the northern hemisphere. Question 6, option A is correct. Question 7, why is the stratospheric temperature is warmer in summer hemisphere? Why is the stratospheric temperature warmer in the summer hemisphere? More cloud cover, reduced ozone, increased UV absorption and higher carbon dioxide. why is the stratospheric temperature is warmer in summer hemisphere? Question 7, option C is correct. In the summer hemisphere, continuous sunlight allows ozone in the stratosphere to absorb more ultraviolet radiation, leading to strong radiative heating, especially that is above a seen above 25 km. Question 7, correct option is C. Now we will go to the question 8. Which season shows a warmer polar stratosphere in the winter hemisphere? Which season shows warmer polar stratosphere in the winter hemisphere? Warmer polar stratosphere in winter hemisphere. So warmer polar stratosphere. So the warmer polar stratosphere, that is around greater than 60 degree warmer. So warmer at 25 Kelvin. So greater than 60 degree warmer. So greater than 60 degree warm. In winter hemisphere, of course, the greater than 60 degree, there will be the warmest temperature, that is warmest temperature, but the hemisphere would be also in winter hemisphere. So in the December, January, February, you can see the here the answer would be option C, that is that shows a warmer polar stratosphere in the winter hemisphere, June, July, August in northern hemisphere. The equatorial lower stratosphere is warmer in December, January, February than June, July, August. Warmer in June, July, August than December, January, February. Same in both seasons, and coldest region overall in both seasons. So equatorial lower stratosphere is yes. 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 Uh, qu- Question number 8, the warmer polar stratosphere. So you can see here at the pole in June, July, August. There is 25 June, July, August polar stratosphere. The temperature is 25. 25. Okay. Yes. Yes. No. Yes. So there then the 8 is, sorry for the mistake. Yes. Yes. This would not be correct. Yes, 8 I'm option was I told wrong. So for the 8 there would be at 25 kilometer height. The mean the temperature, sorry, I have to write this. At the 25 kilometer height, the northern south, 25 kilometer height, here the temperature is around at 80 degree north. is temperature around 190 sorry 200 Kelvin, and 80 degrees south, the temperature is around, suppose this is around 240 250 240 Kelvin at December, January, February. And in June, July, August at 25 kilometer, 80 degree north has temperature of around 80-degree north has temperature around this white, this is 225 Kelvin around, and 80 degree Kelvin, 80 degrees south is temperature around, suppose 190 Kelvin. So the question was, which season? Warmer polar stratosphere in winter hemisphere. Warmer polar stratosphere in winter hemisphere. So winter hemisphere polar stratosphere will be winter hemisphere. So can you elaborate the answer? What are you saying? Hello. Hello. Yes. Yes. Okay. Yeah, yes. Mm, yes. Warmer polar stratosphere. But okay. Yes. So is this thing right or wrong? Can you just verify from this plot? At the in the DJF time, at the 25 kilometer altitude, the temperature about at 80-degree north is around 200 Kelvin. This, and at 80 degrees south, the temperature is around 240 Kelvin, 230 to 240 Kelvin. This region. Hmm. Mm, okay. Yes. Then DJ. Then I will discuss this question later. Okay. I'm confusing the whole thing. Okay. Okay. Thank you. Yes. Maybe from where I took these questions, I got wrong, some confusion. Sorry for my misconception. Uh, the equatorial lower stratosphere is warmer in DJF than June, July, August. Warmer in the June, July, August than DJF. Same with bone season. And D is the coldest region overall in both season. So lower stratosphere, we can see lower stratosphere, that is warmer or colder. The equatorial lower stratosphere is warmer or colder. Which time is warmer? That is 50 to 100 millibar. 50 to 100 millibar. This is warmer in which time? This 50 to 100, this region is warmer in which time? Yeah, yes. Slideshow. 50 to 100. This is varying from this 210 to 200. This is also 210 to 200. Yes, this is both are the same. The equatorial lower stratopause is same in both season. Question 9, option C is correct. In December, January, February, tropopause in tropics has the temperature around tropopause around tropical region, that is around suppose 30 degree north and about 15 kilometer in December, January, February. Tropics and around 15 kilometer. This is around 210 to 210. Around question 10 option B is correct, 220 kilometer. And the next question 8 I will discuss later. I could not give the correct answer, or I have some misconception for this. Now for question 11, the warmest temperature at 45 kilometer occur in summer hemisphere polar region, winter hemisphere polar region, equator and subtropics. So at the you can see in this figure that when we are going high above from the 0 to height of 45 kilometer, the pressure is decreasing in some order, that is around 15 degree. There is 1000 millibar is pressure, 1000 millibar pressure, difference you can also see. At 45 kilometer, above the sea level, 45 kilometer above the sea level, where the warmest temperature is seen, that is occur in the southern summer hemisphere polar region, winter hemisphere polar region, equator and subtropics. So the warmest region you can see, warmest region, polar region. So this is occurring at 280 and this is 280. That is occur at the summer hemisphere polar region. So you can see here when there is a summer time, the polar at the 45 kilometer above the sea level, where the pressure is around 1 millibar, there the temperature is 280 Kelvin reaches, and this 280 just alters in two seasons. That is in the when there is a in some hemisphere there is summer time, the this rate contour is seen at the 45 kilometer here, and also in this summer you can see there is rate region at the 45 kilometer. So question 11 option A is correct. And the question 12, the pressure axis is plotted in the linear scale from 1000 to 1 millibar, some 1000 millibar to 1 millibar, logarithmic scale from 1000 millibar to 1 millibar, linear scale from 1 millibar to 1000 millibar, and hybrid height spacious scale. You have to see this figure once again. We should see. This is in the logarithmic scale. So you know that the 1000 millibar is our sea level pressure, or more specifically 1013 point something millibar is the sea level pressure, and the pressure as you going up, this is decreasing, and this plot has been made with the logarithmic pressure axis. Question 12 is option B correct. And question 13, which feature is a signature of the Brewer-Dobson circulation? Warmer tropical stratosphere in summer hemisphere and cold tropical tropopause in both seasons. Warm winter polar stratosphere compared to summer polar stratosphere, and cold equatorial mesosphere. Which feature is a signature of the Brewer-Dobson circulation? Warmer tropical stratosphere in summer hemisphere, cold tropical tropopause in both seasons, warm winter polar stratosphere compared to summer polar stratosphere, and cold equatorial mesosphere. So this is the thing. The Brewer-Dobson circulation moves air upward in tropic, then poleward and downward in the winter hemisphere stratosphere. That downwelling causes adiabatic warming. So winter polar troposphere is warmer than the summer polar stratosphere, even though the winter pole gets less sunlight. So, at a first glance, it might be seen logical to expect that in the summer pole will be warmer because it is getting continuous sunlight, but in the stratosphere, dynamics play a bigger role than the direct sunlight receiving. So the fact is, the at the polar stratosphere is warmer. So the fact is, the winter polar stratosphere is warmer than the summer polar stratosphere. So this is because this happens because of the movement of air tropics to poleward, from tropics to poleward, and here three kinds of effect plays a role. One is the planetary wave forcing, downwelling and adiabatic warming, and summer hemisphere contrast. So the ideas are planetary wave forcing, where large scale planetary waves generated in the troposphere propagate upward into the stratosphere. This waves breaks the winter hemisphere because of the strong westerly stratospheric jets which allow wave propagation. Wave breaking deposits heat and momentum, disturbing the polar vortexes. Wave breaking drives one kind of air circulation known as the Brewer-Dobson circulation. Air rises in the tropics and sinks over the winter pole. As the air sinks, it is compressed by increasing pressure at the lower altitudes. Adiabatic warming occurs. And in the summer hemisphere, stratospheric winds are easterly, which blocks planetary wave propagation from the troposphere. This reduces downwelling. Instead, upwelling occurs, which causes the adiabatic cooling. Despite of strong solar radiation, the net effect in the middle stratosphere is cooler polar summer temperature than the winter. So it is seen that the winter pole is warmed dynamically by downwelling and adiabatic compression, and the summer pole is cooled dynamically by upwelling and adiabatic expansion even under 24-hour sunlight. So for the question 13, option C will correct, and question 14 also with why is the winter polar stratosphere is warmer than the summer polar stratosphere. That is question 13 and 14, both options C are correct. We will discuss the more about these two features, these questions, and what is seen in the question, sorry, 8 I guess, yes, the warmer polar stratosphere in winter hemisphere. This question 8 and question 13 and 14 more elaborately in next classes. So we are giving the just MCQ options correct, but do not discussing. Yes, yes. Uh, you are saying winter hemisphere. Winter hemisphere. Okay. So for the winter hemisphere, you have to look the both two plots, because for the winter hemisphere, the December, January, February, the winter is the summer. Sorry, northern hemisphere, and this changes when there is a June, July, August. So you have to consider both the two plots. Because the December, January, February, for December, January, February, the winter hemisphere is this region, uh, 0 to 90 degree north, and June, July, August, the winter hemisphere is 90 degrees south to this 90 degree or 80 degrees south for the pole winter hemisphere. So then you have to write the temperature, what is the value for the temperature contours. Okay. Yes. So question 13, 14 and question 8. I guess there is some link between question 13, 14, 8, and 8. We will discuss this in the later class after some of the discussion discussed in this lecture videos. And here is the question 15. In June, July, August, temperature at 30 kilometer in the southern hemisphere polar region are about 200 Kelvin. So temperature at 30 kilometer in southern hemisphere polar region. So for this question, you have to go to the southern hemisphere polar region, that is southern hemisphere polar region, that is 80 degrees, around 80 degrees south, and at 30 kilometer, 80 degrees south, 30 kilometer, you are getting around 190, this is 190 200 Kelvin. So the values are, yes, the values would be 200 Kelvin. Question 15, option A is correct. The lowest temperature around 190 Kelvin appear over the summer pole in mesosphere, over the winter pole in lower stratosphere, over the summer pole in mid stratosphere, and over the equator in the lower stratosphere. Question 16. The lowest temperature appear over the summer pole in mesosphere, over the winter pole in lower stratosphere, over the summer pole in mid stratosphere, over the equator in lower stratosphere. So you have to find where is the coldest temperature, that is around this 190 Kelvin. This is for the 30 kilometer. So this is the winter hemisphere, mid stratosphere. Winter hemisphere, mid winter hemisphere. Sorry, winter pole uh, in lower status in stratosphere. Winter pole in lower stratosphere. Question 16, option B is correct. Yes. Question 17. Which hemisphere shows stronger stratospheric temperature gradient between equator and the pole? Summer hemisphere between in both December, January, February and June, July, August. Winter hemisphere in both December, January, February and June, July, August. Equal in both hemisphere, opposite in season. Stronger stratospheric temperature gradient between equator and pole. Question 17, correct answer will be B. You can see in the figure and check why this is happening, why this is the answer, how the contours are changing per kilometer of height from pole to equator. And question 18 is a true or false. A perennial minimum at the equatorial tropopause and a seasonal minima near the polar tropopause is seen during winter for atmospheric temperature. This is true or false? A perennial minimum at equatorial tropopause and a seasonal minimum near the polar tropopause is seen during winter for atmospheric temperature. True or false? Question 18. Question 18 is true. Of course, you can see in this figure that a minima occurs here in the here. One minima occurs here and one minima here. This two times. So there is a perennial minima temperature at the equatorial tropopause. The tropopause over the equator is higher and much colder than at other latitudes, forming is what is known as the tropical tropopause layer cold trap. This minimum persists throughout the year. Near this pole, especially in the winter, there is a seasonal minimum in temperature at the polar tropopause. During the polar winter, the tropopause temperature reaches to its lowest value for the region, marking the strong seasonal cycle. Sorry, so this two region here you can see. This is the two thing. Sorry, I got mistake with this. So this two minima, one minima is in here, and when in the winter time this goes to pole, and of course another this June, July, August, one minimum is here and another minimum is here when there is winter time. So in which the time when there is winter, this region just get shifted. Next question is about the impact of global warming on the regional surface temperature. It is seen that the impact of global warming is uneven, and this the figure has been met from the data of 1981 to 2020, and here for the what is the maximum amount of temperature, what is the temperature rise, has been colored over the world map, and you can see the color trend is 0 for this some region, and also there is minus in some regions also. Some region there is not significant. So what is the uh, so now the questions are the which region has warmed most in between 1981 to 2020? Equator, South America, Arctic, Australia. And then what does the this cross marks indicate on this map? And what is the approximate warming trend over the Indian subcontinent from this map? So now the questions are, so we have to see the 19E. So which region has been warmed most? So the region which is warmed most is the Arctic region, you can see. And what is the cross mark? Cross mark is a not significant warming or cooling. Also there are few regions where there which are cooled, that is in this ocean region, you can see this has been significantly cooled. And next, what is the in the Indian subcontinent, what is the mean rise or the mean trend? That is this color code you have to see, that is around 0.2, 0.4, this 0.2 to 0.4 within it is about 0.3 degrees Celsius per decade. Now we will see the tropospheric lapse rate figure, and we will try to answer few questions. Some questions from the which were asked from the previous figures could not be answered by me. This is my own fault. I also of course accept, and I will try to discuss those answer more elaborately in the next classes. So now the question is, we have to see this you have seen these two figures in week 1 or week 2 content. Now you have to answer. You can see you have seen that the lapse rate is steeper in equator than the higher altitude, because this primarily occurs because of intense solar heating and the strong convective activity in the tropical regions. So the facts are the stronger surface heating at the equator. The equator receives more direct sunlight whole year round, which heats the atmosphere strongly. This intense heating warms the atmosphere, which is present near the surface of the equator, surface of equator region, more than at the stronger at higher latitudes. So a large difference is created in between the surface and the upper troposphere. This temperature gradient translates the steeper lapse rate, which is the rate of temperature, which is the lapse rate, which is the rate of temperature decrease with altitude, and greater convection and the moist content. Warm surface air at equator is less dense and tends to rise vigorously. This process is known as the convection. Rising air cools as it expands with height, contribute to the lapse rate. Additionally, the equatorial region's high water vapor content releases latent heat through the condensation during the ascent process, which influences and partly moderates the moist adiabatic lapse rate, but still results an overall steeper lapse rate relative to the colder region. Less stable atmosphere at equator at middle and high latitudes. Cooler surface temperature and more stable air masses reduce the rate at which the temperature drops with height. Here, stability caused by cold and often drier air reduces the sharpness of the lapse rate. In contrast, equator's atmosphere is generally more stable, allows temperature to decrease more rapidly with height. The environmental lapse rate near the equator tends to be closer to the dry adiabatic lapse rate, which is about 9.8 degrees Celsius per kilometer, due to strong heating and convection, whereas at the higher altitudes it is typically less steeper because of weaker surface heating and less convection. So in summary, from the figure it is seen that the lapse rate is more steeper in the equator due to combined effect from the solar heating of surface, vigorous convection, higher moisture content or higher water vapor content, and here as you go up the lapse rate decreases. And also in the equator, the tropopause, where there is the bend in this temperature profile, is also higher at the equator. At the equator, this is about 15, 16, 17, 18, around 17.5 kilometer. The tropopause is here, and in the 15 degree, you can see it is about 12 kilometer. The tropopause is stating, and in the 80 degree north, it is about 6, 7, 8, 9, around 9. Around 9, this is just tropopause is stating, and also the length of the tropopause is here bigger in 80 degree north, and also in the 80 degree northern region you can see the temperature profile. This also varies because and 80 degree north in the January, the temperature profile starts at there is an temperature inversion seen in the January, and in the February March this is starting from the higher temperature because now the temperature at the northern hemisphere is increasing, and from winter to summer phase it is going. And of course you can see that at 80 degree north the tropopause is about 8 kilometer in this figure. Now here are the questions. Where is the tropospheric lapse rate steepest? We can discuss two questions at a time. Where is the tropospheric lapse rate steepest? Of course, question A is equator. The question A's answer is equator. Lapse rate is steepest as equator. Which season shows the temperature inversion near the surface at 80 degree north? At the winter time, there is inversion near the surface at higher latitude. That is so in the winter means in the January. 22 option will be January. And how does the tropopause altitude vary with latitude? How how does tropopause altitude vary with latitude? Tropopause altitude decreases towards the pole. Question 23, C will be correct answer. Pen. So, question 24 maybe not for from this. Question 24, 25 we can just answer, but those are not related to this question. Which region shows the greatest warming during July to January? This is the Arctic region. And in which hemisphere does the seasonal warming appear stronger? In the northern hemisphere, the seasonal warming appears to be stronger. Which is the tropopause? What is the tropopause temperature near the equator? So for this question, the tropopause temperature near the equator, we have to go to this last figure, of course. We know at this figure that tropopause occurs around 18 kilometer. So you can roughly estimate that is 20 kilometer. At the equator, from this figure you can see the temperature at the 25 kilometer. The temperature is around 200 Kelvin. So the 200 Kelvin is equals to 273 Kelvin is equals to 0 degree Celsius, you know. So from that you can estimate that is around minus 73 Kelvin. So that is around 60 degrees Celsius, minus 60 degrees Celsius. So the tropopause temperature near equator is around minus 60 degrees Celsius. Why is the lapse rate lower in polar region? This is the polar region have the strong temperature inversion, that is temperature increases with height in the lower troposphere during winter. This reduces the average lapse rate because the vertical temperature drop is similar. Question 27, option C is the correct. And question 28, what is the likely cause of intense Arctic warming in this plot? Intense Arctic warming is this plot. Okay, this three questions 24, 25 and 28 were from the previous figure, this figure, impact of warming figure. You know this answer, that likely cause of Arctic warming is the albedo effect, because due to greenhouse gas the snow covered in the Arctic region is decreasing. So this is causing intense Arctic warming. Question 29 and 30. Question 29. At 2 km above atmosphere, the temperature for the parcel of air is 10 degrees Celsius and pressure is 800 hectopascal. What is the potential temperature of this air parcel? At the 2 km above the atmosphere, the temperature for a parcel of dry air is 10 degrees Celsius and the pressure is 800 hectopascal. What is the potential temperature of this air parcel? Yes, potential temperature. Okay, there are different kind of temperatures. Okay, sorry. So there are different types of temperature in the climate studies. First is the virtual temperature. Virtual temperature accounts the effect of water vapor on air density. Moist air is less dense than the dry air at the same temperature and pressure. So the virtual temperature for a dry air would need to match the density of moist air. So the formula for calculating the virtual temperature Tv is equals to actual temperature into 1 plus 0.61 into Q. Temperature is actual temperature will be given in the question, and Q is the specific humidity, that is the what kg of water vapor contained in 1 kg of moist air, and 0.61 is coming from the gas ratio constant. That is the ratio constant of the gas ratio constant for the vapor and the gas ratio constant of the dry air. And this equation is used to calculate the virtual temperature. We are just discussing the equations today. We will discuss how this temperature idea came in the district class. And also there is the equivalent potential temperature. That's formula is written as, this measures the temperature of a air parcel that would have if it was brought dry adiabatically to P0, usually 1000 hectopascal, and all moisture were condensed out, releasing the latent heat. There is a formula of this equivalent potential temperature, that is equals to T P0 by P to the power kappa, and this kappa is equals to R by Cp, and this LV is the latent heat of vaporization, RS is the saturation mixing ratio, and Cp is the specific heat constant at constant pressure. And this equivalent potential the potential temperature, formula for calculating the potential temperature the main formula which is used for potential temperature is equals to theta is equals to P0 by P to the power R by Cp into T. So now in this questions you have given the what is the temperature ambient temperature of the air parcel, and R is the 0.287 kilojoule per kg Kelvin, and Cp is 1.005 kilojoule per kg Kelvin. So you can calculate P. Yes. This formula came from the adiabatic expansion theory, adiabatic theory. We are not discussing that theory. These were discussed in some weekly lecture content, I guess. We are just discussing the math problem. We are not. This is the adiabatic theory from the adiabatic theory and gas law. Yes, this is this. Yes, the thing is this exponential, this factor is close to 1. This is close to 1 for the case, for the some special case. Equivalent potential. Kappa is present, R by Cp, this factor we are considering here. This, yes, this is kappa. This is kappa, R by Cp. Yes. This is from the adiabatic theory and the thermodynamics gas law. I have not discussed that. part yet. Maybe those were discussed in the lectures. You can see. Question 29 was about 302 Kelvin, the answer. Now we should just question 30. Adiabatic lapse rate for the unsaturated parcel of air is greater than mean tropospheric lapse rate, is lesser than mean tropospheric lapse rate, equal to mean tropospheric lapse rate, and depends on latitude of the location. So now you have to know what is the environmental lapse rate and adiabatic lapse rate and their differences. So environmental lapse rate, or the only lapse rate, only tropospheric lapse rate, is the actual measured decrease in temperature with altitude at a specific place in time in atmosphere. So in the environmental lapse rate, or only lapse rate, or only tropospheric lapse rate, is the actual measured decrease of temperature. It is about 6.5 Kelvin per kilometer in the troposphere. Environmental lapse rate or the tropospheric lapse rate depends on weather condition, time and the season, and the moisture contained and the air masses present. This is mainly obtained by the radiosonde data or the aircraft data. And the adiabatic lapse rate has a definition that it is a theoretical rate at which a parcel of air changes temperature with altitude when this air parcel is moved without exchanging heat with its ambient surrounding. This process is the adiabatic process. You know, in the thermodynamics, adiabatic processes where delta Q is equals to 0. That is when you do some work, but there is no heat exchange with the system and its environment. Adiabatic lapse rate for the dry air is about 9.8 Kelvin per kilometer, and adiabatic lapse rate for the moist air is typically low, that is 4 to 7 Kelvin per kilometer. And this moist adiabatic lapse rate of course varies with temperature, because moisture content varies with temperature, you know. This adiabatic lapse rate calculation solely determined by the thermodynamics principle, and this measurement can be done mathematically, adiabatic lapse rate measurement. So adiabatic lapse rate for unsaturated air parcel is greater than mean temperature, greater than mean tropospheric lapse rate, lesser than mean tropospheric lapse rate, equal to mean tropospheric lapse rate, and depends on latitude of the location. So unsaturated air parcel means you can say this is the dry air parcel. You can write the answer in the chat box, or of course. Question 30, option A is correct. Question 30, option A is correct. This is adiabatic lapse rate for the unsaturated air parcel is greater than the mean tropospheric lapse rate. Question 31, the term climate sensitivity typically refers to warming parts per million increase in carbon dioxide, equilibrium temperature change due to carbon dioxide doubling, daily variability of temperature extremes, and response of ecosystems to humidity. The term climate sensitivity typically refers to warming per parts per million increase of carbon dioxide, equilibrium temperature change due to carbon dioxide doubling, daily variability of temperature extremes, and response of ecosystems to humidity. You can write the answer in the chat box, or you can unmute yourself. So this climate sensitivity refers to the increase of equilibrium global mean temperature by doubling the carbon dioxide content. So option B is correct. Equilibrium temperature change due to doubling of carbon dioxide content in atmosphere refers to the climate sensitivity. And question 32, the El Nino oscillation primarily affects global climate through alteration of hard-steel structure, changes in stratospheric ozone, ocean and atmospheric heat exchange in Pacific, and mid-latitude jet stream reversal. Question 32, option C is correct. This is related to the ocean events. The weekly content will discuss this. And this is driven by the change in ocean specific atmospheric exchange, not linked to the stratospheric ozone activity or alteration of hard-steel structure or jet stream reversal. Now there is a question 33. A team of scientists are preparing to launch a high altitude balloon to correct the atmospheric data. At sea level, atmospheric temperature, that is recorded to about 101,325 Pascal. That is about about 101,325 Pascal, and they want to find the pressure conditions at 6 km above sea level. So this is in the terms of hectopascal. We know that is the 100 Pascal is equals to 1 hectopascal. So in the hectopascal unit, this will be 1013.25. So about 1000 hectopascal if you take the integer power point. So this unit was an hectop. So no, this was a millibar unit. Just remember what is the units of the millibar, hectopascal, and the conversions. Now for this question, that this is given that you have your atmospheric pressure, sea level pressure is 1013.25 hectopascal, and there is the typical vertical scale of about 7.6 kilometer, and at 6 kilometer above the sea level, what is the typical pressure? In the Pascal, you have to give the Pascal unit, not in hectopascal unit. So when there is a scale height is given, you know the equation of pressure as a function of Z is equals to pressure P0, pressure is equals to some P at Z is equals to 0, Z0 into exponential minus Z by H. So H is given for the 7.6 kilometer. You have to put Z at 6 kilometer above. P at Z is equals to 0 in Pascal unit is given. So, and you have the three values, and you can find p at z 6 kilometer. So I have computed this. You can just use this formula. This is coming around 46,000 Pascal. Now there is question. Now there is a question 34. If air temperature at the surface near equator is 30 degrees Celsius and the temperature at the equatorial tropopause is around 70 degrees Celsius, at the height of tropopause, assuming the constant lapse rate, that is 6.5 Kelvin per kilometer, uh, the height of tropopause assuming the constant lapse rate of 6.5 kilometer per 6.5 Kelvin per kilometer. So now you can convert this 30 degrees Celsius to Kelvin and minus 70 degrees Celsius to Kelvin. So you will get around get the difference of 100 Kelvin. So per Kelvin there is 6.5 kilometer temperature drop. So the height for the sorry, per kilometer there is 6.5 Kelvin temperature drop. So you can find the height of the tropopause, that is from the 100 by 6.5, that is coming around 15, I guess, that is coming around 15.4 kilometer. Now the question 35 was the same kind of question that were discussed in the previous class. The mean temperature of Jupiter atmosphere is around 165 Kelvin. The mean molecular weight is 2.22 gram per mole and the acceleration due to gravity is 24.8 meter per second square, and the scale height, the gas constant value has been given, and if you can use this equation, and you will get the scale height about 25 kilometer. You know the scale height equation is RT by mg, where R is the typical gas constant, T is the temperature of the atmosphere which is given, m is the mass of the molecule, that is the in the gram per mole unit, and G will be given per meter in the acceleration unit. And if you plug in these values in this equation, you will get the scale height of the atmosphere. So scale height is equals to where there is E time decrease, around 63% decrease of the surface pressure value. Now the next question is the atmospheric constituent that is responsible for half of the greenhouse effect is ozone, carbon dioxide, water vapor, or methane. Yes, this is the atmospheric constituent which is responsible for half of the greenhouse effects is the water vapor. Water vapor is the largest contributor for the natural greenhouse effect, and it is responsible for around 50%, roughly 50% of it, because of its abundance in atmosphere. It strongly absorbs the infrared radiations because of its vibration levels are same wavelength of the infrared radiation. Carbon dioxide, methane and ozones are also contributing factors for greenhouse, but their combined effect is still smaller than the water vapors effect. And question 37, the environmental lapse rate of troposphere is around 6.5 Kelvin per kilometer, 8 Kelvin per kilometer, 7.5 Kelvin per kilometer, 9.8 Kelvin per kilometer. You know the environmental lapse rate is 6.5 Kelvin per kilometer. And next question is, environmental lapse rate is equal to adiabatic lapse rate. Question 38, false. Yes, question 38 is false. And the scale height h is a constant. Atmospheric in constant atmospheric pressure increases exponentially with altitude. The scale height is constant in constant atmospheric pressure. Atmospheric pressure increases with exponentially with altitude. Is this true or false? Of course, this is also false. 39 is false. We have seen that P is equals to P0 at Z is equals to 0 into exponential minus Z by H. H is the scale height constant. Question 40. Which of the following statements is untrue or false for stable atmosphere? Vertical transport of water vapor and energy is difficult. Buoyancy driven convection currents are weak. Lead to large scale cloud formation and precipitation event. Parcel of air will sink back down when lifting force is removed. Question 40, we have to discuss all these effects. Question 40 I am leaving for today. Question 40 I will discuss in the next class. This will take much time. Question 41, saturation vapor pressure as a function of temperature is given by question 40 I am leaving also for 8, 13 and 14. These questions I am leaving. Some questions from the previous week and also for this week I am leaving due to my own inability of course and also time constraint. We will try to discuss those in the next classes. Question 41, saturation vapor pressure as a function of temperature is given by the ideal gas law. This statement is true or false? We know the saturation vapor pressure graph, that is this. This was from the Clausius-Clapeyron equation, not by ideal gas equation. Ideal gas equation we know PV is equals to N at T equation. So this statement 41 is false. Question 42. Currently, the global mean atmospheric temperature at the surface of Earth is approximately 59 degree Fahrenheit. Is this true or false? You have to remember the Celsius to Fahrenheit conversion for this question. And this is Celsius to Fahrenheit conversion. You can test that this is around 15 degrees Celsius, which is about 59 degree Fahrenheit. This statement is true. Question 43. The total mass present per unit area in a column of air between the surface and the 250 hectopascal is around dash kg per meter square. The total mass per unit area in a column of air between the surface and the height where the pressure is 250 hectopascal is um, about. So we have to remember this formula. That is the mass per unit area is equals to PS, that is the pressure at the sea level, minus P at the top, that is pressure at the top of the atmosphere, by G. Here there will be a minus because mass cannot be negative, this mass will be positive. So by this formula, this is coming around 7,000 something kg per meter square. We will post this along with this weekly lecture PPTs, and you can check. But this is to remember the formula for the mass per unit area is equals to minus PS by minus of PS by P top by G. Now for the question 44. What is the possible consequences of an increase of increase in atmospheric water vapor content? This is a multiple options correct question. Question 44 is a multiple option correct question. Water vapor acts as a heat trapping greenhouse gas similar to carbon dioxide. Yes, this is a correct option. Increased water vapor enhances cloud formation, which can influence Earth's radiation balance. Of course, this is also correct, and it helps to negative feedback that cools Earth's surface. This is not true. This has a positive feedback. It is a greenhouse gas. This increases the water vapor content in atmosphere. It increases heat content in atmosphere. And question 44, water vapor participates in positive feedback loop that amplifies global warming. Yes, question 44 option 4 is correct. So here the three options are correct, A, B and D. Question 44, three options are correct, A, B and D. Yes, the options are correct. Now question 45. Which of the following is true? The latitudinal temperature difference between rising parcels of air at lower latitudes are far larger at higher altitudes than those at higher latitude. The latitudinal difference between rising parcel of air at higher latitudes are far larger at higher latitude than those at lower latitude. The latitudinal difference between rising air parcels of air at lower latitudes are far larger at lower altitude than the higher latitude. The latitudinal temperature difference of rising parcel of air at higher latitude are far larger at lower latitudes than or lower altitudes than lower latitudes. Question 45, option C is correct, but I will not discuss this question today. Question 45, the answer C is given correct, but I will not explain this. Okay, this is okay, this I will discuss in the next class. Question 45 will be discussed in the next class along with question 40, this kind of thing. Now there's question 46. Higher latitudes receive higher average isolation due to attenuation and beam spreading. This is true or false? Higher latitudes receive higher average insolation due to attenuation and beam spreading. This is true or false? This option is false. Question 46. Because at the higher latitudes, the less average insolation is received because the beam is becoming spread. The beam of the sunlight is becoming spread and larger atmospheric path is seen at the higher latitude, not more. Yes. Yes, this is for the solar radiation beam, and the higher, if you just plot this thing. Suppose here is the sun, here is the earth, and here is your atmosphere. So here you can just take this. This is one beam. Now here, this is the main. The beam is being attenuated by greater amount of atmosphere here, and here is the lower amount of atmosphere. It is being attenuated, and beam is here being spreaded. So higher latitude receive higher average insolation due to attenuation and beam spreading. This statement is false because it will suffer, the solar beam will suffer more attenuation due to larger atmosphere in its field or in its path. So here this will be lower average insolation. Now the question is, the angle between plane of ecliptic and earth axis is around 23.5 degree, 90 degree, 66.5 degree and 0 degree. We know plane of ecliptic, that is the plane at which the earth and sun are here. We know Earth's axis is tilted at 23.5 degree normal to the ecliptic plane. So between ecliptic plane and the Earth's axis, the angle is 90 minus 23.5, that is around 66.5 degree. So option C is correct for question 47. Now for yes. Okay. Yes. So this is the, suppose this is the sun, and this is the earth, but earth and sun are in same plane, but earth axis is rotating. This is sun axis, this is earth axis, and this is the rotation axis of earth. Now this axis and this rotation axis has the 23.5 degree, around 23.5 degree. This is the tilt of earth. Now they are asking what is the plane of ecliptic and the earth's axis. This is 90 minus 23.5 degree, around 66.5 degree. Okay, 66.5 degree. Now Question 48. Which of the following factors contribute to lower average temperature at higher latitudes compared to equator? Increased atmospheric attenuation of solar radiation, greater brim spreading of the solar radiation, higher concentration of greenhouse gases at higher latitude, and the earth being significantly closer to sun during high latitude summer. Which of the following factors contribute to lower average temperature at higher latitude compared to equator? Here you can eliminate the option 4 and also this option higher concentration of greenhouse gas is at higher altitude is also not right. Here the option A and B are the correct. High latitude receive less intense sunlight because sun's rays have to travel longer path through atmosphere, so it strike more atom or molecules in this path, and its attenuation is larger, and it strikes the earth's surface at the lower angle, that is known as the beam spreading. The other two options are not correct. Greenhouse gases are found to be well mixed globally, uh, and it has not a significant variation with latitudes. And earth sun, if the one area of earth or one region of earth is more tilted toward the sun, it would be, or more closer to the sun, it would receive greater sunlight, so there is no means of the lower temperature in that area. So for the question 48, the C and D are not correct. A and B are the correct. Question 49. Question 49 is which of the following conditions indicate the vertically unstable atmosphere for an unsaturated air parcel? We will discuss 49 in the next class. We are leaving it. Question 49. I am leaving many questions today for the next discussion. I will try to discuss those in the next class, of course. Question 50. Sun rays falls on earth parallel to the plane of equator. Is this true or false? This is of course false, because earth has a tilted axis. Sun rays do not fall on earth on the equator parallelly. Question 50, option B is correct. Question 49 I am leaving. So this ends my discussion today, and we will discuss the more questions and the questions which I missed today due to my inability, and in the next class. So if you have any suggestion or if you have anything to discuss, you can tell. Anything to ask or discuss? I'm stopping the presentation. Okay. Yes. Okay. Okay, the main thing was I had done the calculation, but yes, okay. I will. Okay. Okay. Okay, thank you. Anyone have any other question? Anyone have any question? Then we will take the next class if in the next week in the usual session from the Sunday 6 to 8. I will discuss the questions mainly which were not covered today. Thank you for joining. Uh, okay, if anyone have any question, he or she can unmute yourself and tell or what you want from this session, what thing you want to be discussed in this session. Okay. Uh, so today I am stopping this session. Thank you for joining. Okay. Thank you. Yes, thank you.